This video is how to determine a rate law given experimental data. So in your notes packets, there is a part of your notes before this part that I'm showing you right now on the screen. It's got some graphs and things about first order reactions. I would like you to read the book, please, and take the notes there, and we can discuss those in class, but I need you to get those from the book first. I want to show you how to do an actual problem given data. How do we determine the rate law? So in this practice problem, it says one of the reactions occurring in the ozone layer in the upper atmosphere is NO plus O3 yields NO2 plus O2. All right, so then we've got data. We've got our concentration for our NO reactant. We've got a concentration for our O3 reactant. And then we've got this change in concentration over time. And another way to say this right here would be the rate. So we've got multiple sets of data. So if the concentration of NO is one thing and the O3 is something else, our rate is whatever that value is. And you can see there's a whole bunch of those. So what we're going to do is we're going to use this to figure out what our orders are for each reactant. So remember our overall, or our maybe kind of our generic equation would be rate equals K and the concentration of our reactant. So we've got NO to some exponent, and then our concentration of O3 to some other exponent. So we're trying to figure out what those exponents are. So I'm going to look at the data here, and I'm going to find a spot where one reactant concentration changes at a time. Dealing with just one variable, just like in a science experiment, change one thing at a time. So for example, in the NO, when it's this first one here and here, these two are the same. Okay, so if that's constant, look at what happens to the O3. So if I go from 3 times 10 to the 6, or negative 6, to 6 times 10 to the negative 6. So what does this change by? Well, this changed by a factor of 2. I'm going to write times 2, right? 3 times 10 to the negative 6 times 2 will equal 6 times 10 to the negative 6. Another way to think about this, or to calculate it if it's not obvious like this one, would be to take the bigger one divided by the smaller one. All right, so when our concentration changes by a factor of 2, what happens to the rate? Okay, so look at the rates here. Look at these two. Okay, and here might be one that's not as obvious. So I'm going to type in 1.32 times 10 to the negative 4th divided by 0.660 times 10 to the negative 4th. And what I find is this is also increased by a factor of 2. So if you remember in a previous video, we talked about if you increase this by a factor of 2, what happens to your rate, right? And we said if your M was 2 was squared, right, it would be increased by a factor of 4 because 2 squared is 4. If it was a factor of 1, it would stay the same, etc. So what we're looking for here is let's plug these in. So let's say we have our concentration of O3. Let's say it's, well, not let's say it's right, twice as big. To what power? It's going to equal 2. So you have to think about, well, what exponent would have to be? Well, in this case, that exponent would have to be, therefore, n would have to equal 1, because 2 to the first equals 2. So we've just figured out that the O3 is first order. So now let's do this with data where the O3 stays constant and the NO changes. And we can see that right here, right? These two are the same. So what happens to these two? Well, this increases by a factor of 2. So what happens to the rate? So if I take the 3.96 divided by 1.98, I also get a factor of 2. So this is saying now that we have the same thing. We have 2 to that power will equal 2. Therefore, M equals 1. So now we've just found out that the NO concentration is also first order. So what is our equation? Right, if I go down here, what is our rate law? So the rate law is going to be rate equals K, concentration of NO to the first power, and the concentration of O3 to the first power. So there's the first part. Second part says, what's the rate constant? So K equals what? So here's where we're going to plug numbers in and just solve for K. So I'm going to do a little algebra here first, and I'm going to say, okay, well, K equals the rate divided by your concentration of NO and your concentration of O3. And now what I'm going to do is I'm going to plug in any set of data. So I could do any set of data points here. I'm just going to pick the bottom one. I don't know why my screen's doing that. Sorry. All right, so 5.94 times 10 to the negative fourth. And I'm going to plug in the units because remember, K has specific units depending on the order. So this is overall second order. So if you have that memorized, great. If you don't, I'm just going to do the math here. So rate is moles per decimeter cubed per second. All right, and then I'm going to divide it by 3 times 10 to the negative sixth moles per decimeter cubed. And 9 times 10 to the negative sixth moles per decimeter cubed. Okay, so I can see unit-wise, moles per decimeter cubed, one on top, the only ones on top, and one of the bottom ones cancel out. So if I type this in my calculator, I'm going to get 2.20 times 10 to the seventh. I change it to scientific notation because it's kind of a big number to write. And then my units will be, let's see, decimeters cubed over moles seconds. Because if I take this right here, right, we have 1 over seconds over moles over decimeters cubed. If I do the reciprocal, I do it times both sides. Right, these cancel. And so this, I simplified as this, which you could also write as moles to the minus 1, decimeters cubed, seconds to the minus 1. So 2 parts to your answer. Here's the rate law, and here's your rate constant. All right, we will do another example in class. Please make sure you read the book and get the top part of the notes that are in your packet.